Hey everyone, and welcome to our deep dive today. We're taking a close look at something you probably saw in chemistry class. You know that colorful chart on the wall? The periodic table.
Oh, yeah. Definitely brings back some memories.
But there's so much more to it than just a list of elements, right? We'll unpack its history, the logic behind it, and we'll uncover some of the cool stories hidden within it. I mean, did you know that the arrangement of the periodic table actually tells us about how an element behaves?
It's true, the periodic table is kind of like this giant puzzle. And the way all the pieces fit together really does reveal some fundamental truths about the universe.
I like that. A giant puzzle. So let's start putting this puzzle together. Let's go back in time to the 1800s. Dmitri Mendeleev. He's working with about 60 known elements at the time, a lot less than we have now. And he's trying to make sense of it all. To organize them in a meaningful way, what was he thinking?
Well, Mendeleev had this incredible insight. He realized that when he arranged the elements in order of increasing atomic weight, certain properties just kept popping up. They seemed to repeat periodically. It was like a rhythm or a pattern in the elements. And that's what led him to create the first periodic table.
And get this, he even left gaps in his table. He predicted that new elements would be discovered, new elements that would fit perfectly in those gaps, and he even predicted their properties.
That's right, incredible foresight.
And it turned out he was spot on. For example, he predicted this element that would be similar to silicon. Years later, germanium is discovered, and its properties were almost exactly as Mendeleev described.
It really was a remarkable achievement, not just a lucky guess. This really solidified the power of the periodic table as a predictive tool.
Yeah, he had a glimpse into the future of chemistry, but his table wasn't perfect, was it? There were some kinks to work out, what didn't quite fit.
Well, one of the biggest challenges for Mendeleev was that some elements seemed out of place if you just looked at their atomic weights, like tellurium and iodine. Tellurium is heavier than iodine, but its properties suggest it should actually come before iodine on the periodic table.
So atomic weight alone wasn't enough.
Exactly.
It wasn't the whole story.
No, it wasn't. And this is where Henry Moseley enters the picture. In the early 1900s, he made this groundbreaking discovery. It revolutionized our understanding of the periodic table. He found that arranging elements by their atomic number, the number of protons in their nucleus, that solved many of the issues that Mendeleev had run into.
Yeah. So the atomic number, that's the key.
Yeah.
And that brings us to the periodic table we use today. But let's be honest, it can still feel a little overwhelming at first glance.
Right.
All those rows and columns and colors.
Yeah, it can be a bit daunting.
So can you walk us through how it's organized so our listener can really grasp the brilliance of its structure?
Absolutely. Imagine the periodic table like a well-organized city. The horizontal rows are called periods, and each period represents a different energy level or electron shell. As we move down the table, it's like adding floors to a building, and then the vertical columns are called groups. Elements in the same group, they share similar chemical properties because they have the same number of valence electrons.
Valence electrons, those are the ones in the outer shell, right?
Yeah,
Ready to interact and form bonds with other atoms.
precisely.
That's where the action is. So by arranging the elements this way, by periods and groups, we get this incredibly powerful tool for understanding how they'll behave.
You got it. Knowing an element's address on the periodic table, it helps us predict so much about it, from its reactivity to the types of bonds it will form.
It's like having a cheat sheet for understanding chemistry.
Exactly.
So it's not just about memorizing the elements and their symbols. It's about seeing the bigger picture, those underlying patterns that connect everything.
It's like a code waiting to be deciphered.
Exactly. And to crack this code even further, we need to delve into those four distinct blocks of the periodic table, the S, P, D, and F blocks. They're based on how electrons fill different types of orbitals within an atom.
Right.
It gets a little more complex, but stay with us.
Think of orbitals like rooms in an electron hotel. The S, P, D, and F blocks. They tell us which rooms are being filled as we add electrons.
Okay, so different rooms, different orbitals. And these different rooms give rise to unique characteristics for each block.
That's right.
Okay, let's unpack these blocks one by one, starting with the S block. Groups 1 and 2, what kind of elements do we find there? What makes them special?
The S block is home to the alkaline earth metals. And these elements are known for being highly reactive. Think of sodium reacting explosively with water, or the bright light produced by magnesium when it burns.
Oh, right. So the S block is where the fireworks are. Lots of energy, lots of reactivity. Okay, what about the P block? What's going on over there? In groups 13 to 18.
The P block is a very diverse group of elements. We've got metals, nonmetals, metalloids. It's a real mix. We find essential elements like carbon, nitrogen, and oxygen here. They play such a crucial role in life as we know it. The air we breathe, food we eat. We also find the halogens in this block. like fluorine and chlorine, super reactive, and with a ton of applications in industry and medicine.
Wow. So the P block is like the variety pack of the periodic table, a little bit of everything.
Yeah.
Okay, now on to the D block, groups 3 to 12. What makes these elements stand out?
The D block is where we find the transition metals, elements like iron, copper, gold, silver. They're known for their variable oxidation states, which means they can form ions with different charges. And this leads to a whole range of colorful compounds, from the deep blue of copper sulfate to the vibrant green of nickel chloride.
So the D block is where we find those elements that have been prized throughout history, not just for their beauty, but also for their practical uses. And finally, we have the F block, often separated from the main body of the periodic table down at the bottom. What's the story with these elements?
The F block is home to the lanthanides and actinides. And many of these elements are radioactive. They have these unique electronic structures that lead to interesting magnetic and optical properties, and some of them are even used in nuclear reactors in high-tech applications, like lasers and magnets.
So the F block is a little bit more mysterious, a bit more elusive, but with tons of potential. And it's amazing to think that all of these elements, from the most reactive alkali metal to the heaviest radioactive actinide, they all follow these predictable patterns in their behavior. These patterns are known as periodic trends.
Right.
And they emerge from the way the periodic table is organized.
Exactly. These trends help us understand not only the individual properties of elements, but also how they relate to each other.
It's like a grand tapestry, woven together by the fundamental principles of atomic structure.
I like that, a tapestry.
Okay, so let's dive into some of these trends. We've got atomic radius ionization, energy, electronegativity. They can be a little tricky to grasp at first, but they're worth understanding. They unlock a deeper level of insight into the elements.
Absolutely. Think of them as clues that help us solve the mysteries of chemistry. Clues that allow us to predict how elements will behave in different situations.
Love a good mystery. So let's start with atomic radius. Basically, a measure of the size of an atom, right?
Yeah, you can think of it as the distance between the nucleus of an atom and its outermost electron shell.
Okay, so does the size of an atom change as we move across or down the periodic table?
It absolutely does. There are clear patterns, and these patterns are determined by two main factors: the number of electron shells and the strength of the attraction between the nucleus and the electrons.
Okay, so two main factors in play. Let's break it down. What happens to atomic radius as we move down a group on the periodic table?
Well, as we move down a group, we're essentially adding more electron shells, like adding layers to an onion. The outermost electrons are further away from the nucleus, so the atomic radius increases.
Makes sense. More layers, bigger atom. What about as we move across a period from left to right? What happens to atomic radius then?
As we move across a period, the number of electron shells stays the same, but the number of protons in the nucleus increases. So the positive charge of the nucleus is getting stronger, and it pulls the electrons in tighter. So as we move across a period, the atomic radius actually decreases. It's like squeezing the atom, making it more compact.
Interesting. So the size of an atom isn't just about how many electrons it has. It's also about how strongly the nucleus is pulling on those electrons. It's a tug of war.
Exactly.
Now, what about ionization energy? That sounds a little intimidating. What is it exactly?
Ionization energy is the energy required to remove an electron from an atom. It's the energy needed to overcome the attraction between the nucleus and the outermost electron.
Okay, so a high ionization energy means it's really hard to rip an electron away from an atom.
You got it. And just like atomic radius ionization energy
Yeah.
follows these predictable trends across the periodic table.
Okay, let's see if I can predict this one. As we move down a group, the outermost electron is further away from the nucleus, so it should be easier to remove right.
Exactly. Ionization energy decreases as we move down a group. Those outer electrons are like kids on a long leash. They're less tightly bound to the nucleus.
Makes sense. But what about as we move across a period? Is the trend the same or different?
As we move across a period, the ionization energy generally increases. Remember, the nucleus is getting stronger as we add protons, so it holds onto those electrons more tightly. It's like shortening the leash, making it harder to pull those electrons away.
Got it. So ionization energy increases across a period. It's all about that tug of war between the nucleus and the electrons. Now on to electronegativity. That one sounds a bit more intense. What does it measure?
Electronegativity is a measure of an atom's ability to attract electrons in a bond. Think of it as how much an atom wants to hog the electrons in a shared bond.
I'm picturing a tug of war between two atoms over a pair of electrons. So if an atom has a high electronegativity, it's pulling harder on those electrons.
Exactly. And just like ionization energy, electronegativity generally increases as we move across a period. Those atoms with stronger nuclei are better at attracting electrons, even when those electrons are being shared with another atom.
Okay, so electronegativity increases across a period. But what happens as we move down a group? Does it increase or decrease?
Electronegativity generally decreases as we move down a group. Remember, as we add electron shells, those outermost electrons are getting further away from the nucleus, so they are less strongly attracted.
So these trends, atomic radius ionization, energy, electronegativity, they all help us understand how an element is likely to behave in a chemical reaction.
Precisely. They're like clues that reveal the chemical personality of each element, and they allow us to predict how it will interact with other elements.
And this is where things get really interesting, because these trends aren't just abstract concepts, they have real-world implications. For example, electronegativity differences are crucial in battery technology. The greater the difference in electronegativity between the two elements in a battery, the greater the voltage or potential difference the battery can generate.
Right.
So the bigger the electronegativity difference, the more powerful the battery.
That's the idea. And ionization energy is closely related to the reactivity of metals. Metals with low ionization energies, like those alkali metals in the SOT block, they tend to be very reactive because they lose electrons easily. That's why they're often found in compounds rather than in their pure elemental form.
So the periodic table isn't just a chart on a classroom wall. It's a tool for understanding and predicting the behavior of matter in the real world. And it's amazing to think that all of these trends and patterns, they emerge from the arrangement of elements based on something as fundamental as the atomic number.
It really is a testament to the power of scientific observation and the human ability to find order and meaning in the complexity of nature.
But even with all this order, there are still some exceptions, right? Elements that don't quite follow the rules. It wouldn't be science without a little bit of mystery.
Of course, the universe is full of surprises, and the periodic table is no exception. There are a few elements that buck the trends, and those exceptions often lead to interesting insights and a deeper understanding.
Can you give us an example? What kind of exceptions are we talking about?
Well, for instance, we said that ionization energy generally increases as we move across a period, but there's a slight dip in ionization energy between beryllium and boron. Beryllium actually has a slightly higher ionization energy than boron, even though boron has one more proton in its nucleus.
That's strange. Why would that be?
It has to do with the arrangement of electrons within those atoms. Beryllium has a filled s orbital, which is a very stable configuration. Removing an electron from beryllium disrupts this stability, so it requires more energy. On the other hand, boron has one electron in its p orbital, which is slightly less stable.
So it's almost like beryllium is holding onto those electrons a bit tighter because they're in a more stable, balanced configuration.
Exactly. And these kinds of exceptions can be found throughout the periodic table. They challenge us to think critically about the underlying principles and to refine our understanding of how atomic structure influences chemical behavior.
And speaking of challenges, there's still some debate in the scientific community about the placement of certain elements, particularly in the F block, right?
Yeah. The F block is a bit of a puzzle within a puzzle. There are different ways to arrange the lanthanides and actinides, and there's no single universally accepted solution. Some argue for a more traditional arrangement based on historical precedents, while others advocate for a revised layout that better reflects the underlying electronic configurations of these elements.
So it's a reminder that science is an ongoing process of discovery and refinement. The periodic table isn't just a static chart, it's a dynamic framework. It continues to evolve as our knowledge expands.
And that's what makes it so fascinating. There's always more to learn, more to explore, more to debate. It's a never-ending quest for understanding the building blocks of the universe.
And who knows, maybe one day you, dear listener, will discover a new element and contribute to the evolution of the periodic table. But even if you don't, you can still appreciate the incredible insights that this seemingly simple chart offers. It's a story of scientific ingenuity, a symphony of elements, and a testament to the power of the human mind to find order and meaning in the complexity of nature.
And that, I think, is the true beauty of the periodic table. It's a window into the fundamental principles that govern the universe, a reminder that there's always more to discover, and an invitation to keep asking questions and exploring the world around us with curiosity and wonder.
This has been an amazing journey through the periodic table, and I hope you've gained a deeper appreciation for its elegance, its power, and its endless capacity to inspire.
Me too. It's like squeezing the atom, making it smaller.
Okay, so the size of an atom isn't just about how many electrons it has. It's also about how strongly the nucleus is pulling on those electrons. It's like a constant tug of war.
Right, exactly.
Okay, let's move on to another friend. Ionization energy. What is that?
Ionization energy is the energy that's required to remove an electron from an atom. You can think of it as the energy needed to overcome the attraction between the nucleus and that outermost electron.
So a high ionization energy means it's hard to pull that electron away.
Exactly. And ionization energy also follows these predictable trends, just like atomic radius.
Okay, so let's think about this. As we move down a group, the outermost electron is further from the nucleus, so shouldn't it be easier to remove?
You got it. Ionization energy decreases as we move down a group. Those outer electrons are less tightly bound to the nucleus.
Okay, that makes sense. What about as we move across a period? Does ionization energy increase or decrease?
As we move across a period, ionization energy generally increases. Remember, as we add protons, the nucleus gets stronger. It holds on to those electrons more tightly.
So it takes more energy to remove an electron.
Exactly.
Got it. Ionization energy increases across a period. Okay, so we've covered atomic radius and ionization energy. Now let's talk about electronegativity.
Okay.
What does electronegativity measure?
Electronegativity is a measure of an atom's ability to attract electrons, specifically electrons in a bond. You can think of it as how strongly an atom wants to pull those shared electrons towards itself.
So if an atom has high electronegativity, it's like winning that tug of war for electrons.
Exactly.
Okay, and how does electronegativity change as we move across the periodic table?
Just like ionization energy, electronegativity generally increases as we move across a period. Those atoms with stronger nuclei, they're better at attracting electrons.
Even when they're sharing those electrons with another atom in a bond? Okay, so electronegativity increases across a period. What about as we move down a group?
Electronegativity generally decreases as we move down a group. As we add electron shells, the outermost electrons are further from the nucleus and less strongly attracted.
So these trends, atomic radius, ionization energy, and electronegativity, they all help us to understand how an element will behave.
Absolutely.
They give us insight into how it might react with other elements.
It's like they reveal the chemical personality of each element.
And this is what makes the periodic table so powerful. These trends aren't just abstract concepts. They have really important implications in the real world.
Right.
For example, electronegativity differences are crucial in battery technology. The greater the difference in electronegativity between two elements in a battery, the greater the voltage or potential difference that battery can generate.
That's right.
So a bigger electronegativity difference means a more powerful battery.
That's the idea. And ionization energy is also important. It's closely related to the reactivity of metals. For example, metals with low ionization energies like the alkali metals in the S block, they tend to be very reactive because they lose electrons easily. And that's why we often find them in compounds rather than in their pure elemental form.
It's amazing how all these trends and patterns emerge from something as fundamental as the atomic number. It really shows how much information is packed into the periodic table.
Absolutely. The periodic table is more than just a chart. It's a tool for understanding and predicting the behavior of matter in the real world.
But even with all this order and predictability, there's still some exceptions, right? Elements that don't quite follow the rules.
Of course, the universe is full of surprises, and the periodic table is no exception. There are a few elements that buck the trends.
Can you give us some example?
Sure. We said that ionization energy generally increases as we move across a period, but there's actually a little dip in ionization energy between beryllium and boron.
That's interesting. So what's going on there?
Well, it has to do with the arrangement of electrons in those atoms. Beryllium has a filled orbital, which is a very stable configuration. Removing an electron from beryllium disrupts that stability, so it requires more energy. Boron, on the other hand, has one electron in its orbital, and that's slightly less stable.
So beryllium is holding on to those electrons a bit tighter because they're in that more stable configuration.
Exactly. And these kinds of exceptions remind us that we always need to think critically about the underlying principles.
Right.
They help us refine our understanding of how atomic structure influences chemical behavior.
And speaking of challenges, there's still some debate in the scientific community about the placement of certain elements, particularly in the Pfeff block.
Yeah, the Pfeff block is a bit of a puzzle within a puzzle. There are different ways to arrange the lanthanides and actinides, and there's no single solution that everyone agrees on.
So there's still room for debate and discussion.
Absolutely. Some scientists argue for a more traditional arrangement based on historical precedents. Others prefer a layout that better reflects the underlying electronic configurations of those elements.
So it's a reminder that science is a process.
That's a process of ongoing discovery and refinement.
We're always learning and updating our understandings. The
Exactly.
periodic table isn't just a static chart on the wall. It's a dynamic framework that continues to evolve.
And that's what makes it so fascinating. There's always more to learn, more to explore, more to debate.
It's a never-ending quest to understand the building blocks of the universe.
Exactly.
And who knows, maybe one day you, dear listener, will be the one to discover a new element and contribute to the evolution of the periodic table.
I hope so.
But even if you don't, we can all appreciate the incredible insights that this seemingly simple chart offers. It's a story of scientific ingenuity, a symphony of elements, and a testament to the power of the human mind to find order and meaning in the vast complexity of nature.
Beautifully said.
It's truly remarkable how much we can learn about the universe just by studying this one chart.
I agree.
So as we wrap up this part of our deep dive, I want to encourage you to keep exploring the periodic table. It's a treasure trove of information, and it's a testament to the power of human curiosity and ingenuity. And it really highlights how much we can learn about the universe just from this one chart.
It's true. It's not just about the elements themselves. It's those underlying principles that govern how they behave. The periodic table really gives us this visual representation of those principles. It helps us understand the dance of electrons within atoms.
Speaking of electrons, we talked about the SPD and F blocks of the periodic table. And these blocks are based on how electrons fill those different types of orbitals, those regions of space around the nucleus, where electrons are most likely to be found. But how does this all connect to quantum mechanics?
Well, it might sound intimidating, but it's not as complicated as you might think. Quantum mechanics is the study of how energy and matter behave at the atomic and subatomic levels.
Yeah.
And it turns out the arrangement of electrons within atoms, which is reflected in the periodic table. It's governed by those laws of quantum mechanics.
So the periodic table is like a bridge between that macroscopic world where we see and touch elements and the microscopic world of atoms and electrons.
Exactly. It connects those two realms. And it helps us understand how the properties of matter really emerge from that quantum world, like the shape and energy of electron orbitals, the SPD and F orbitals that we've been talking about. They're determined by quantum mechanics. And those shapes and energies directly influence things like an element's reactivity, its bonding behavior, even its color.
So those orbitals aren't just some abstract concept. They have real-world consequences that we can observe. Okay, that makes sense. So before we wrap up this deep dive, I want to circle back to some of the limitations of the periodic table. We talked about Mendeleev's early version and how it wasn't perfect. How does the modern periodic table, the one we use today, how does it address those limitations?
Well, one of the biggest improvements is the way it handles isotopes. Remember, isotopes are atoms of the same element, but they have different numbers of neutrons and therefore different atomic weights. Mendeleev's table really struggled with this, but the modern table solves it beautifully.
How so?
Well, because isotopes are the same element. They have the same number of protons, that's their atomic number. They all occupy the same position on the periodic table, regardless of their atomic weight.
That's much more logical. It recognizes that the real identity of an element is in the number of protons, not the number of neutrons. What other improvements did the modern table bring?
What also addressed those anomalies that Mendeleev encountered. Remember how some elements seemed out of place based on their atomic weight?
Right, like tellurium and iodine.
Exactly. Their properties suggested one order, but their atomic weights said something else.
But when we arrange elements by atomic number, it all falls into place.
Precisely. The modern periodic table gives us a more accurate picture. It better reflects the true chemical nature of the elements,
It really shows the progress of science.
how we keep refining our understanding, building on the work of those who came before.
But even the modern periodic table isn't set in stone, is it? It's still evolving.
Absolutely. Science is a journey.
A constant quest for knowledge.
The periodic table continues to be a focal point for exploration and debate. For example, there are still discussions about the best way to represent certain elements, especially in the F block. And there's always the possibility of discovering new elements. That could extend the periodic table even further.
I love that. The idea that there's still so much out there to discover.
It's the beauty of science. It's a never-ending journey.
So, as we wrap up our deep dive today, I hope you've all gained a deeper appreciation for the periodic table. It's more than just a chart in a textbook, it's a window into the heart of matter. It's a reminder that there's always more to explore. Keep asking questions, keep that curiosity alive, and maybe one day you'll be the one to make an amazing discovery, a discovery that changes our understanding of the universe.